So continuing on our theme and counting in two ways. One situation when that becomes very advantageous is when you're dealing with numbers that have natural representations geometrically. So we've seen these before. Of course, maybe the most obvious are the square numbers. These are like 1, 4, 9, 16, 25, 36, and so on. We can think of these geometrically as arrays of dots. So this would be an example of 3 squared. I could just think of a 3 by 3 square. We also have the cubes. And here you can think of them along the same way by going up a dimension. But for me, that's a little trickier. I don't like to think in 3 dimensions if I can help it. I really like things to be rendered on the plane. And so I can think of taking 3 squares and just stacking them. And if it was 4, then I just put 4 in a row. So this is how I would think of 3 cubed. And of course, one thing that we've been seeing in a lot of the examples are the triangle numbers. These come up often. The triangle numbers are 1, 3, 6, 10, 15, 21, and so on. We have derived twice now the formulas for them. And again, the identity is really just counting in 2 ways. This is how you would maybe, if you were going to make them sequentially, you just add the next number to the next triangle number to get them. Or if you wanted to jump to the 100th triangle number, it would be more efficient to use this formula. And again, we could think about these geometrically. This would be the 3rd triangle number, which is 6. Okay, so what's the problem that we want to really think about here? I'm going to combine all of these concepts into one problem. So here's our problem. What we want to do is we want to show the difference. Now, whenever we're doing combinatorics, differences can be really interesting. Negative numbers are interesting to try to make combinatorial. The difference between the squares of 2 consecutive is important, consecutive triangle numbers is a cube. Okay, there's our statement. That's kind of a surprising statement, I think. I'd like to do some examples just so that we can see that that's the case. So let's look at the triangle numbers and do some consecutive ones. Well, we have 3 squared minus 1 squared. What is that? That's 8, which is also known as 2 cubed. Okay, that checks out. Let's do 6 squared, which is 36, minus 3 squared, which is 9. And when we do that, we get 27, which is 3 cubed. Okay. We could take 100, and we could subtract 36. We get 64. And we could just kind of keep going with this. If we take 15 squared minus 10 squared, that's going to be 125, which is indeed 5 cubed. So it looks good. But as we saw from Poya's example, we don't want to bank on that. What we want to do is we want to think about this geometrically, and it can give us more intuition for why this might be true. Why is it true that when we take these differences of these triangle numbers, why are we going to get a cube? So let's take a bunch of dots. Here I'm doing a very specific example. I'm doing this example here. So just to kind of keep things grounded, I want to think about 10 squared minus 6 squared is equal to 4 cubed. And I'm going to do it very specifically to this example, and then I'm going to think about how I could generalize this to make a true statement that's more general. Okay, so let's think, I've got the purple dots. So here I've got 10 squared dots. And let's do this. Let's take away 6 squared of them. So let's see if I can do that without screwing up too much. I believe I have grabbed a square of size 6. So let's delete this. Delete. Okay, so now we have 10 squared minus 6 squared dots. That's what's left. And we want to think about how is this 4 cubed? Now remember, for me, 4 cubed is going to be 4 groups of 4 by 4 squares. And I can already see the first 4 by 4 square is right here. And why is it? Because 10 minus 6 is 4. Why? Why is 10 minus 6 4? Well, it has to do with this rendition of the triangle numbers. So let me give these guys names. I'm going to let this guy be T sub n. And now what I'm going to do is I'm going to think of, I've got T sub 4 minus T sub 3 squared Okay, that's how I'm thinking of 10 squared minus 6 squared. And now here is my 4, which I can think of here as maybe n. Now keep in mind that what have I got down here? What have I got left? Well, this is going to be T4 minus T3, right? This is T4 minus T3. So this is T3. This was my T3 by T3, which is my 6 by 6 square that I deleted. The whole thing is my T4 by T4. T3 minus T4 is 4. In general, Tn minus Tn minus 1 is equal to n by this formula here. We just add n to get to the next one. And now remember, I'm looking for for n groups of n squares. So I want to think about T3. Now I got to think about, this is one of my 4s. So there's one of my 4 by 4s. But I need 3 more of them. Well, how many of them do I have down here? Okay, I have T3, which is 6. Well, again, let me use this formula for it. So I can use this formula and say, okay, what is T3? It's going to be 3 times 4 divided by 2. And then, of course, my width here is 4, okay? So I've got 3 divided by 2, 4 by 4 grids, right? That's what I've got over here. And I have the exact same thing up top. So I have the same thing, 4 by 4 up here. So if I think about what that adds up to, okay, the 3 halves plus 3 halves is going to give me 3. So what do I get? I get my 1 4 by 4 here, and then I get 3 more 4 by 4s by combining these two. So I get 4 times 4 times 4 dots, right? And another way I could think about that is, well, here's my 3 halves that I've sort of divided these into. These extra little spurious bits here and here get combined to make my 4th group of 4 by 4. Okay, and now if I want to make this rigorous, I've sort of played around with this just to give you the intuition. I think about things in terms of these t's, okay? Well, this triangle number is going to be a tn squared minus tn minus 1 squared. And what it looks like to me is that what I'm going to get is n cubed. Now, this is something that I can prove. I can prove this. Again, how? By coming back over here and using this identity that I've already proven. That's the key to it that I realized down here. I wrote the 6 in terms of a 4. So in order to do this, right, I think about the grid, and I'm just going to split it up and count the regions the way that I've done. So I get one central region here, which is going to be my n by n block. I get an n by n in the corner. And then I'm going to get a bottom piece that is going to be, let's see, n minus 1 by n over 2 by n. And I'm going to get a top piece that's n minus 1 n over 2 by n. And then when I add all of these up, what does that give me? That gives me an n by n plus n minus 1 n over 2 by n plus the same thing again. And now I just combine those guys, so I get n by n plus n minus 1 n by n, which equals n times n by n, which is my n cubed. So that's one way that if you have these sort of problems, you can think about them geometrically and prove these identities. There's a homework problem that you have, which is going to be effectively proving this statement, but in a slightly different way. So you can do it by thinking about counting things in 2 ways, or you can do it by induction. It's your choice, whatever you're most comfortable with.